The Holocene Extinction, otherwise referred to as the Sixth Extinction or Anthropocene Extinction, is a name for the ongoing extinction event of species during the present Holocene epoch, mainly due to human activity. A large number of extinctions span numerous families of plants and animals, including mammals, birds, amphibians, reptiles and arthropods. Although 875 extinctions occurring between 1500 and 2009 have been documented by the International Union for Conservation of Nature and Natural Resources, with widespread degradation of highly biodiverse habitats such as coral reefs and rainforest, as well as other areas, the vast majority are thought to be undocumented. According to the species area theory and based on upper bound estimating, the present rate of extinction may be up to 140,000 species per year, making it the greatest loss of biodiversity since the Cretaceous Paleogene extinction event. The Holocene extinction includes the disappearance of large land animals known as megafauna, starting between 9,000 and 13,000 years ago, the end of the last ice age. Megafauna outside of the African continent that did not evolve alongside humans prove highly sensitive to the introduction of new predation, and many died out shortly after early humans began spreading and hunting across the earth. The extinction of the mammoths allowed grasslands they had maintained through grazing habits to become birch forests. The new forest and the resulting forest fires may have induced climate change. Such disappearances might be the result of the proliferation of modern humans. These extinctions, occurring near the Pleistocene-Holocene boundary, are sometimes referred to as the Quaternary Extinction event. There is no general agreement on where the Holocene, or Anthropogenic, extinction begins, and the Quaternary Extinction event, which includes climate change resulting in the end of the last ice age, ends, or if they should be considered separate events at all. Some have suggested that anthropogenic extinctions may have begun as early as when the first modern humans spread out of Africa between 100,000 and 200,000 years ago, which is supported by rapid megafaunal extinction following recent human colonization in Australia, New Zealand and Madagascar, in a similar way that any large, adaptable predator moving into a new ecosystem would. In many cases, it is suggested even minimal hunting pressure was enough to wipe out large fauna, particularly on geographically isolated islands. Only during the most recent parts of the extinction have plants also suffered large losses. The ecology of Homo sapiens has been noted as being that of an unprecedented global super-predator that regularly preys on the adults of other apex predators and has worldwide effects on food webs. Extinctions of species have occurred on every land mass and ocean, with many famous examples within Africa, Asia, Europe, Australia, North and South America, and on smaller islands. Overall, the Holocene extinction can be characterized by the human impact on the environment. The Holocene extinction continues into the 21st century, with overfishing, ocean acidification and the amphibian crisis being a few broader examples of an almost universal, cosmopolitan decline of biodiversity. It has been suggested human activity has made the period following the mid-20th century different enough from the Holocene to consider it a new, geological epoch, known as the Anthropocene, which will be considered for implementation into the timeline of Earth's history by the International Commission on Stratigraphy in 2016. Human influence on extinction. Extinction of animals, plants, and other organisms caused by human actions may go as far back as the late Pleistocene, over 12,000 years ago. There is evidence that abrupt climate change has especially played an enormous role in the extinction of larger mammals. However, while previous mass extinctions were due to natural environmental causes, research shows that wherever on Earth humans have migrated, other species have gone extinct, and human population growth, most prominently in the past 2 centuries, is regarded as one of the underlying causes of extinction. In terms of how humans have contributed, 3 major factors include the increased global concentration of greenhouse gases, affecting the global climate, oceanic devastation, such as through overfishing and contamination, and the modification and destruction of vast tracts of land and river systems around the world to meet solely human-centered ends, thus replacing the original local ecosystems. Other related human causes of the extinction event include deforestation, hunting, pollution, the introduction in various regions of non-native species, and the widespread transmission of infectious diseases. At present, the rate of extinction of species is estimated at 100 to 1,000 times higher than the base, or historically typical rate of extinction, and also, the current rate of extinction is, therefore, 10 to 100 times higher than any of the previous mass extinctions in the history of Earth. It is also the only known mass extinction of plants. The abundance of species extinctions considered anthropogenic, or due to human activity, have sometimes been collectively called the Anthropocene Extinction. The Anthropocene is a term introduced in 2000. It is now posited by some that a new geological epoch has begun, characterized by the most abrupt and widespread extinction of species since the Cretaceous Paleogene extinction event 66 million years ago. In The Future of Life, E.O. Wilson of Harvard calculated that, if the current rate of human disruption of the biosphere continues, 1/2 of Earth's higher life forms will be extinct by 2100. A 1998 poll conducted by the American Museum of Natural History found that 70% of biologists believe that we are in the midst of an anthropogenic extinction. Numerous scientific studies, such as a 2004 report published in Nature, and papers authored by the 10,000 scientists who contribute to the IUCN's annual Red List of Threatened Species, have since reinforced this conviction. Extinction of the megafauna in the late Pleistocene. The evidence of all previous extinctions is geological in nature, and shorter geological time scale is of the order of several 100,000 to several million years. Even extinctions caused by instantaneous events such as the impact of the asteroid in Chicxulub, which is currently the best example, extend the equivalent of many human lives due to complex ecological interactions that were triggered by the event. 3 hypotheses have been proposed to explain the extinction of megafauna in the late Pleistocene. Of these, only 2 have much scientific credibility. Although Ross McPhee proposed that a hyperdisease may have been the cause of the extinction, a study by Lyons et al. Demonstrated conclusively that a hyperdisease was unlikely to have caused the extinction. The 2 main theories to the extinction are climate change and human hunting. The climate change theory has suggested that a change in climate near the end of the late Pleistocene stressed the megafauna to the point of extinction. Some scientists favor abrupt climate change as the catalyst for the extinction of the megafauna at the end of the Pleistocene, but there are many who believe increased hunting from early modern humans also played a part, with others even suggesting that the 2 two interacted. In the Americas, a controversial explanation for the shift in climate is presented under the Younger Dryas impact hypothesis. Megafauna was once found on every continent of the world and large islands such as New Zealand and Madagascar, but is now almost exclusively found on the continent of Africa, with notable comparisons on Australia and the islands previously mentioned experiences population crashes and trophic cascades shortly after the earliest human settlers. It has been suggested that the African megafauna survived as they evolved alongside humans. The timing of South American megafaunal extinction does not appear to correspond to human arrival, although the possibility of whether human activity at the time may have impacted the global climate enough to cause such an extinction has been suggested. It has been noted, in the face of such evidence, Homo sapiens is unique in its ecology as an unprecedented global superpredator, regularly preying on large numbers of fully grown terrestrial and marine apex predators, and with a great deal of influence over food webs and climatic systems worldwide. Anthropogenic impact on climate during the Holocene. In order to constitute the Holocene as an extinction event, scientists must determine exactly when anthropogenic greenhouse gas emissions began to measurably alter natural atmospheric levels at a global scale and when these alterations caused changes to global climate. Employing chemical proxies from Antarctic ice cores, researchers have estimated the fluctuations of carbon dioxide and methane gases in the Earth's atmosphere for the late Pleistocene and Holocene epochs. Based on these studies, general argumentation of when the peak of the Anthropocene occurred pertains to the time frame within the previous 2 centuries, typically beginning with the Industrial Revolution, when greenhouse gas levels were recorded by contemporary methods at its highest. However, scientists that are employing a variance of archaeological and paleoecological data argue that the process is contributing to substantial human modification of the environment spanned many thousands of years ago on a global scale and thus not originating as early as the Industrial Revolution. Gaining popularity on his uncommon hypothesis, paleoclimatologist William Rudiman in 2003 stipulated that in the early Holocene 11,000 years ago, atmospheric carbon dioxide and methane levels has fluctuated at a different pattern than the Pleistocene epoch before it. He argued that the patterns of the significant decline of CO2 levels during the last ice age of the Pleistocene inversely correlates to the Holocene, where there has been dramatic increases of CO2 around 8,000 years ago and CH4 levels 3,000 years after that. The correlation between the downfall of CO2 in the Pleistocene and the uprising of it during the Holocene implies that the causation of the spark of greenhouse gases into the atmosphere are due to the growth of human agriculture during the Holocene, such as the anthropogenic expansion of land and irrigation. Recent extinctions described are well documented, but the nomenclature used varies. The term Anthropocene is a term that is used by a few scientists, and some commentators may refer to the current and projected future extinctions as part of a longer Holocene extinction. The Holocene-Anthropocene boundary is contested, with some commentators asserting significant human influence on climate for much of what is normally regarded as the Holocene epoch. Other commentators place the Holocene-Anthropocene boundary at the Industrial Revolution, while also saying that formal adoption of this term in the near future will largely depend on its utility, particularly to Earth scientists working on late Holocene successions. Agriculture. Human civilization flourished in accordance to the efficiency and intensification of prevailing subsistence systems. Local communities communities that acquire more subsistence strategies increased in number to combat competitive pressures of land utilization. Therefore, the Holocene developed competition on the basis of agriculture. The growth of agriculture has then introduced newer means of climate change and pollution. Recent investigations about hunter-gatherer landscape burning has a major implication for the current debate about the timing of the Anthropocene, and the role that humans may have played in the production of greenhouse gases prior to the Industrial Revolution. Studies on early hunter-gatherers raises questions about the current use of population size or density as a proxy for the amount of land clearance, and anthropogenic burning that took place in pre-industrial times. Scientists have questioned the correlation between population size and early territorial alterations. Ruddiman and Ali's research paper in 2009 makes the case that early farmers involved in systems of agriculture used more land per capita than growers more later in the Holocene, who intensified their labor to produce more food per unit of area, arguing that agricultural involvement in rice production implemented thousands of years ago by relatively small populations have created significant environmental impacts through large-scale means of deforestation, while a number of human-derived factors are recognized as potentially contributing to rising atmospheric concentrations of CH4 and CO2. Deforestation and territorial clearance practices associated with agricultural development may be contributing most to these concentrations. Globally, climate change in the early Holocene was distinguished prior to the last glacial maximum 15,000 years ago, which then started the current period of the glacial retreat, where climate started to increase significantly 11,000 years ago. The Holocene epoch contained a vast number of temperature fluctuations that can be dated from the warm period of the Holocene climatic optimum in 5,000 to 3,000 BC that consisted of temperatures that were 1 to 2 degrees Celsius warmer than today, to the more recent emergence of the Industrial Revolution. During this period came the development of ancient civilizations of the earliest Homo sapiens and the growth of agriculture due to the increase of tropical regions. Deepening the understanding of the anthropogenic impact in the early Holocene is a vital factor for analyzing interglacial climate instability due to their involvement in producing of atmospheric carbon dioxide. Methodologies of the Holocene climatic optimum to undermine the present and future human-induced climatic changes. Climatologists and paleontologists have correlated the increases of temperatures with the variations of solar radiation exposed to certain latitudinal Earth bands during the early Holocene, thus believing that the Holocene warming was solar in origin, where only certain parts of the world experienced warmer climates during seasons such as summer. Moreover, scientists have conducted numerous oceanic sediments that can be dated back to the Holocene climatic optimum, and discovered drastic increases of sea levels and the sea level high stands. This evidence of drastic increases of sea levels indicates that the deterioration of ice cores is crucial to understanding how the Holocene climatic optimum began and how it played as one of the major transgressions during the Holocene maximum. As speculations of how the Holocene climatic optimum began remain scientifically unclear, impurities in gaseous chemistry inside these ice cores have been conducted as a valuable method of obtaining evidence of abnormal temperature fluctuations. The Nile River showed to have a greater volume and much larger in the Holocene than what it is today, and the Sahara to have been more fertile. This in turn led many anthropogenic hypotheses to claim that more tropical territories encouraged agricultural processes. However, there is greater complexity as to whether such changes are heavily caused by anthropogenic effects on climate because of limited methods that can directly identify an empirical correlation. Prehistoric extinctions. Although significant debate exists as to how much human predation and indirect effects contributed to prehistoric extinctions, certain population crashes have been directly correlated with human arrival. Australia was once home to a large assemblage of megafauna, with many parallels to those found on the African continent today. Australia's fauna is characterized by primarily marsupial mammals, and many reptiles and birds, all existing as giant forms until recently. Humans arrived on the continent very early, about 50,000 years ago. The extent human arrival contributed is controversial. Climatic drying of Australia 40,000–60,000 years ago was an unlikely cause, as it was less severe in speed or magnitude than previous regional climate change, which failed to kill off megafauna. Due to the older time frame and the soil chemistry on the continent, very little subfossil preservation evidence exists relative to elsewhere. However, continent-wide extinction of all genera weighing over 100 kilograms, and 6 of 7 genera weighing between 45 and 100 kilograms occurred around 46,400 years ago, and the fact that megafauna survived until a later date on the island of Tasmania following the establishment of a land bridge suggests direct hunting or anthropogenic ecosystem disruption such as fire stick farming as likely causes. The first evidence of direct human predation leading to extinction in Australia was published in 2016. Dromaeotheridae, an entire family of giant birds. Though around the size of emus, they are actually more related to ducks than other waterfowl. Analysis of burned eggshells in Genyornis newtoni, which stood around 7 feet tall, suggested human consumption. As of yet, this is the most reliable direct evidence of human predation on Australian megafauna. Diprotodon, giant relatives of wombats. Zygomaturus, a marsupial superficially resembling a rhinoceros. Holotherium, a large marsupial herbivore. Phascolonus, a giant wombat. Palocestes azul, a marsupial tapir. A highly diverse assemblage of kangaroos. These include giant species from several genus, including Macropus, Simostheneurus, Steneurus and Protemnodon. Other unique kangaroo radiations include Procoptodon galea, a hoof-toed giant short-faced kangaroo, and Proplea piscicilians, an omnivorous kangaroo. Winambi, a 5 to 6 meter long Australian constrictor snake. Thylacleo carnifex, a lioness-sized marsupial carnivore. Varanus priscus, a giant predatory monitor lizard. Zaglossus hacketi, a giant species of echidna. Quincana, a 5 to 6 meter long predatory terrestrial crocodile. Extinctions in Australia continued from original settlement until today in both plants and animals, whilst many more animals and plants have declined or are endangered. North and South America, there has been a debate as to the extent to which the disappearance of megafauna at the end of the last glacial period can be attributed to human activities by hunting, or even by slaughter of prey populations. Discoveries at Monte Verde in South America and at Meadowcroft Rock Shelter in Pennsylvania have caused a controversy regarding the Clovis culture. There likely would have been human settlements prior to the Clovis culture, and the history of humans in the Americas may extend back many thousands of years before the Clovis culture. The amount of correlation between human arrival and megafauna extinction is still being debated. For example, in Wrangel Island in Siberia, the extinction of dwarf woolly mammoths did not coincide with the arrival of humans, nor did megafaunal mass extinction on the South American continent, although it has been suggested climate changes induced by anthropogenic effects elsewhere in the world may have contributed. Comparisons are sometimes made between recent extinctions and the Pleistocene extinction near the end of the last glacial period. The latter is exemplified by the extinction of large herbivores such as the woolly mammoth and the carnivores that preyed on them. We know that humans of this era actively hunted the mammoth and the mastodon, but it is not known if this hunting was the cause of the subsequent massive ecological changes, widespread extinctions and climate changes. The ecosystems encountered by the first Americans had not been exposed to human interaction, and may have been far less resilient to human-made changes than the ecosystems encountered by industrial-era humans. Therefore, the actions of the Clovis people, despite seeming insignificant by today's standards, could indeed have had a profound effect on the ecosystems and wildlife, which was entirely unused to human influence. The following species, among many others, became extinct in this period: Doedicurus, a giant armadillo; American cheetah, American lion; Holoceles primogenus, pygmy mammoth, woolly mammoth and the local Columbian mammoth; mastodons, Eremotherium, Smilodon, saber-toothed cats; Teratorns, a group of birds that includes some of the largest flying animals of all time. Caribbean human arrival around 6,000 years ago is correlated with the extinction of many species. Examples include many different genera of ground and arboreal sloths across all islands. These sloths were generally smaller than those found on the South American continent. Megalignus were the largest genus at up to 90 kilograms. Acratosnus were medium-sized relatives of modern two-toed sloths endemic to Cuba. Amagonus also of Cuba, Neocnus and many others. Giant huchas, Cuban coney, Protomys, Cuban giant owl. Pacific Islands. Recent research, based on archaeological and paleontological digs on 70 different islands, has shown that numerous species became extinct as people moved across the Pacific, starting 30,000 years ago in the Bismarck Archipelago and Solomon Islands. It is currently estimated that among the bird species of the Pacific, some 2,000 species have gone extinct since the arrival of humans, representing a 20% drop in the biodiversity of birds worldwide. Among the extinctions were Sylviornis, a giant galliform bird from New Caledonia; Mekosuchian crocodiles from New Caledonia, Fiji and Samoa; Maurlania turtles on Lord Howe Island and New Caledonia; Gavialis papuensis, a marine crocodilian from the Solomon Islands; Mediterranean islands, pygmy hippos of Cyprus, Crete, Malta and Sicily; Balearic Islands, cave goat of Majorca and Minorca; a diverse assemblage of dwarf elephants of several islands, including Cyprus, Sicily, Malta and Crete; giant swan of Malta, giant dormouse, Minorcan giant dormouse, Majorcan giant dormouse; Sardinian pigher of Sardinia and Corsica.